Good morning, students. Hoping that you have read the lesson. Let's continue with other types of forces. Be attentive and watch the entire video carefully as we have homework at the end of each video. Let us observe gravitational force. We observe that a ball kicked upwards always comes down to the ground. A fruit detached from the plant falls on the ground. This is because earth pulls them downwards. This pull of the earth is due to a force called gravity. When we lift a dumbbell, we apply a force upwards against the pull of the gravity. Similarly, if an object is thrown upwards, there exists a force which pulls it down towards the earth. Because of this, it falls down on the ground. We call this force as gravitational force. Every object on the earth or close to the earth will experience a gravitational pull. The force of gravity is not just due to the attraction of the earth. It is a force of attraction that exists between any two bodies or masses everywhere in the universe. The earth is so massive and huge that all the other objects close to the earth are attracted or pulled towards it. The force which acts between two bodies when the bodies are not directly touching each other is called force at a distance. These forces can be explained by using the concept of a field. Let us visualize the magnetic field. Take a bar magnet, put it on a table. Take a white drawing sheet, place it over the bar magnet. Now take some iron fillings, sprinkle them on the paper. Now tap the table gently with pen or pencil. Observe the changes. In this activity, we observe that in a small space around the magnet, iron filings set themselves in a pattern because they are affected by the magnetic force of the field created by the bar magnet. So the pattern represents the magnetic field. The space around the magnet where its influence can be detected is called the magnetic field. We learn that every magnet has an invisible magnetic field around it. This field is made up of lines of force that attract magnetic material such as iron fillings. The fillings form a pattern as they line up in the direction of the magnetic lines of force. Thus we say that a field is a region in which a force can be experienced by another object placed at any point in that region. Practically, many forces can act simultaneously on a single body. For example, consider an object placed on a horizontal floor. In this situation, two forces act on the object, where one is the gravitational force and the other is normal force, which acts vertically upwards and vertically downwards respectively. In this case, the forces acting on the object are equal in magnitude and opposite in direction. Hence, there exists no change in the state of the object. Technically, the net force on the object is said to be zero, as the state of the object does not change. The sum of all forces acting on an object is called net force. Imagine that the same object is placed in a lift which is accelerating. In this case, the object is in non-uniform motion. So the net force acting on the object is not equal to zero. When two forces act on a body, as in the above case, one of the forces should be greater than the other to set the body in motion. The strength of a force is usually represented by its magnitude. The direction of a force is as important as its magnitude. We represent the magnitude and direction of force using arrows. Let us do an activity observing the effects of the net force. Choose a heavy object like a table that you can move only by pushing hard. Try to push it. Observe the changes. Now, ask your friend to push in the same direction along with you. Observe the changes. We observe that it is easier to push the table when you take the help of your friend. The force applied by your friend added to the force exerted by you results in both forces being applied on the table in the same direction. The total forces applied by both of you makes it easier to move the table. Now ask your friend to push the table from the opposite direction to you. Observe the direction in which it moves. We observe that the net force on an object is zero if the two forces acting on it in opposite direction are equal. Finally, we learn that all forces have both magnitude and direction. While adding forces, the direction of forces have to be taken into account. When forces act on a body along a straight line and they are in the same direction, the net force is taken as the sum of all forces acting on the body. The sign convention must be used to add forces. The force F1 directed towards right could be taken as positive and the force F2 acting towards left could be taken as negative. If F1 is greater than F2, F net will be equal to F1 minus F2. Finally, we conclude that if the two forces act in the opposite directions on an object, the net force acting on it is the difference between the two forces. The object at rest moves in the direction of the net force acting on it. Dear children, we will continue more about net forces in our next video. Please do the assigned homework. Draw a flow chart showing different types of forces. Read the part of the lesson covered so far, from starting of the lesson to activity 9. Thank you children. Stay safe.